Hi everyone, and welcome to Understanding ASTM E74 Calibration Certificates. Our company, Morehouse Instrument Company, we have a purpose statement, and that purpose is we create a safer world by helping companies improve their force and torque measurements. You are here today, obviously, or you're watching this recording, and we're here to help. To help you by educating on what matters. Today, specifically, we are going to talk about the ASTM calibration certificates and understanding them in more detail, and go over some of the uncertainty, metrological traceability, and some other things. My name is Henry Zumbrun. I've been the president of Morehouse for over the last 5 years, and been with the company for well over 2 decades. What we do, we are a manufacturing company that produces force calibration equipment and adapters. This equipment is used in industry to measure force. We have the state-of-the-art force and torque calibrations laboratories and offer calibrations at a very high level of accuracy. Here's a picture of our dead weight machine. Looks a little different now as we made some structural modifications and improved some things on it. Though this picture was taken in 2004, and we offer dead weight primary standards calibrations accurate to better than 20 parts per million of applied force to 120,000. Other force calibrations offered up to 10 meganewton or 2.25 million pounds are known to within 0.1%. So that's what we do there. On torque, we have the second most accurate torque standard in the world that was purchased from NPL way back in National Physical Laboratory in England, way back in 2010. For torque, we have uncertainties of better than 25 parts per million. Really, really super low uncertainties there. So today, as I said, we're going to discuss calibration certificates and ISO IEC 17025 requirements, including metrological traceability, very important there, and ASTM E74. We're going to break down the LLF, which is a lower limit factor, resolution, how to calculate resolution, calibration coefficients, and curve fittings. The outcome or the desire it would be that you as a participant will be able to have knowledgeable discussions, what is required on their current certificate of calibrations, the proper language to use, and understand the basic math behind the calculations. So we have that. We also have some additional material. This presentation is available in PDF, and we have technical paper on adapters, highly recommended. You can get everything right, and then you don't use the same adapter, and the output or the deflection's different, and then you can't replicate what we do in our lab. So we do a calibration, and we give you the expected performance of that device at the time of calibration. Now you go, as the end user, you would go and derate that. You would use it different temperatures, different conditions, machines that are not as plumb level square rigid. So really, really important to get the adapters right, because they will change the deflection. They can change the line of force, and not getting them right is going to yield a lot. That when we say that expected performance, and I say you derate it, not getting them right can result in really large measurement errors of up to probably 0.5% on some different cells and adapters. Then we have a paper on uncertainty propagation. If you want to know how to do uncertainty propagation from dead weight the whole way down to 3 tiers down, dead weight from load cell calibrated in a dead weight, put it in the cal machine, calibrated then another cell, and then put that in another machine. And then we have a technical paper on ASTM E74 and ISO 376. They are not the same. So those are some three, maybe worthwhile reading material that you have. So here's what's we're starting with. We said we were going to talk about ISO IEC 17025, and here, understanding the calibration certificates. When the calibration report is issued, we must follow these requirements. If you have an accredited cal, doesn't matter if it's ASTM, single run, dual run, accuracy, whatever, we need to follow these requirements. And here's basically, I have this section highlighted because it says the date of issue of the report. And, this is the section we missed. We try to get everything. Section J is where we recently got a deficiency, as we missed this one in the new standard. Really, we forgot to add it to the list of things that needed changed in our program is what happened. So the current certificates we have now have the date of issue of the report. It is almost all the time, it is the same as the calibration date. Typically, the process that we have is the date it's issued, it goes for review. The review signs off on it. That's when it's printed. So, but no, here's the list: name and address, other things. When we start looking at sample certificates, we'll go over more of these. So we have to follow those. And in addition, here's some additional sections. When a calibration report is issued, we must follow the requirements of the standards. We're in accordance with these. And here are some other things that are on here that I have highlighted. These aren't things we missed. These are things that are important. For Section 841, the measurement and certainty of the measurement result presented in the same unit as the measurand or in a term relative to the measurand, e.g. percent. A statement identifying how the measurements are metrological traceable. That's really important here. We're going to discuss it. And then 7843, a calibration certificate or calibration label shall not contain any recommendation on the calibration interval except where this has been agreed with the customer. So if a customer calls us and how we handle ASTM E74 calibration, we say, do you want your recalibration dates to be in accordance with ASTM E74? ASTM E74 has specific guidance on the interval. If the customer says no, then they have to tell us what they want the calibration date to be. So therefore, we put on the certificate customer suggested date. If they want it in accordance with ASTM E74, then we put calibration date in accordance with the ASTM E74 standard. Now, I would highly recommend that anyone listening to this, and if they are following ASTM E74, to have their calibrations due date assigned per the ASTM E74 standard. Now, if you're using the E74 standard to do other cals but aren't really following the E74 standard, that's a different story. Some people like to do it. It's a legally traceable, well-documented procedure that is very good for more load cells, force measuring devices, force measuring instruments that it's being used for, because it really does give the expected performance. It's a lot better than a 10-point calibration without any type of rotation. So the one thing we discuss here is a statement identifying how the measurements are metrological traceable. And then you look at the VIM, which defines metrological traceability as the property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So we start with SI units. It's kind of like the tip of the iceberg there, the SI units, and then we start going down different levels. NMIs, primary standards, accredited labs, force measurement. And when I say that, I break it down here in a little bit different. So if we look at measurement uncertainty as like a mountain or a pyramid, the base units are we start with the SI. The measurement uncertainty data is cumulative from one level of the hierarchy to the other. And when using force, the load cell should be calibrating using measurement standards traceable to SI through a National Metrology Institute, NMI, recognized under the CIPM MRA. This recognition is necessary as some NMIs cannot provide traceability. Per the NIST website, metrological traceability requires the establishment of an unbroken chain of calibrations to a specified reference standard, typically national or international standards, in particular realization of the measurement units of the International System of Units, SI. NIST assures the traceability to SI. The next tier in the pyramid is a primary reference laboratory. This is like us, Morehouse Instrument Company. We're traceable to SI is validated by NIST calibrations on several deadweight force machines. Morehouse provides metrological traceable force transducer calibrations to SI units by applying a relatively known force using deadweight primary standards. And thus, when we start following this, and we look at recognition under, for the NMI under the CIPM MRA, when we start following this, you see, so we're going to send our weights, send most of our weights to NIST to be calibrated for force. They're going to be adjusted for gravity. They're going to be adjusted for material density, air buoyancy. NIST is going to do that calibration. Now, we can't get better than NIST. NIST is going to send that weight back, and it's going to deviate, or it's going to have a bias of probably somewhere in 4 to 5 parts per million per weight. And then we're gonna go put all these weights back in our machine, and we're going to start doing repeatability tests required by our required by ISO IEC 17025, and we're going to follow the GUM for measurement uncertainty. And when we start doing this, obviously NIST can achieve a better level than us on uncertainty, and then that data is cumulative as far as every level down gets bigger and bigger. So when we look at this, we look at traceability here, we see NIST, this is for K equals 1, that's one standard deviation. We look at this, NIST is 4 to 5 parts per million. Morehouse is right here, this is what we are, 008. Accredited calibration suppliers are 0.02, working standards and field measurements. These are typical for force, and as you can see, they get larger and larger. Now, most people will report at K equals 2, and to do that, you just multiply by 2. We're going to talk a little bit more about that later and how that works, because you really should use the Welch-Satterthwaite equation to get the 95% confidence. So we go here, we look at force. This is a nice chart on the NIST website. Force is a derived unit. The SI base unit for force are mass, time, and length, as shown in this illustration here. You can see force is right here for those looking. It's the Newton, the guy that dropped the apple on his head. And there you see kilograms times meters per second squared. So there, that is your mass, time, and length. The formula for force is really mass times acceleration. Using these base unit, the CIPM / BIPM defines 1 Newton as the force required to accelerate 1 kilogram to 1 meter per second in a vacuum. There's your S squared per second. It almost when you read it, it doesn't look right, because it looks like you may have typed something in twice, but you haven't, and that's the formula, again, found on the NIST website, really good. And then we go from there. So we've dealt with measurement uncertainty and how that works. Now we're going to start dealing with the calibration report. When a calibration report is issued, we must follow the requirements of the standards we are calibrating in accordance with. And we go back to ISO IEC 75, a statement identifying how measurements are metrologically traceable. So here, we look at this and we say, right down here, look at this. This calibration was performed using measurement standards traceable to SI through a National Metrology Institute, NMI, such as the United States National Institute of Standards and Technology. Why do we say this? Because on our torque certificates, we're traceable through NPL. We're not traceable through NIST, because NIST does not do torque. And it is essential to have a chain of traceability in which uncertainty is propagated correctly. However, traceability is not to NIST. A lot of people like to say NIST traceable. That is wrong. You can easily correct that. They want to see NIST. Our customers, a lot of them want to see NIST. Therefore, you just write that statement on your certificate. No one will complain. When they say, I want NIST traceable cal, you say, no problem. We're gonna issue a calibration was performed using measurement standards traceable to SI through a national metrology instrument, such as the United States National Institute of Standards Technology, NIST. No one is going to refute this. So when, traceability is not to NIST, it's to SI through NIST. And when calibrating load cells, many laboratories fail to get metrological aspects correct and improperly state NIST traceable master standards. That is wrong. Or traceability to NIST, which is wrong. At Morehouse, we have seen all sorts of incorrect usage of NIST traceability. I bought a torque wrench off of eBay, or not eBay, I bought a torque wrench off of Amazon one time, and I got a little piece of paper with it that said, this is traceable to NIST. Just a little tiny piece of paper, probably was 2 inches high by 4 inches wide, and that's all that said on it. This serial number, blah, 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 is traceable to NIST. Great. Thank you. So next time, really, what we're looking for here is the next time you see NIST traceable statement, question it. As the statement is not correct, it would be best if you ask how far away the lab is from NIST in regard to metrological traceability. Because really, if we're propagating uncertainty correctly, they could be 20, 30 steps away. Guess what that means? That means really, really high uncertainties. And the term uncertainty means doubt. And if it's really, really high, how confident are you going to be in your measurement result? So you really need to follow this logic and look at that chain of traceability and see how far it is away and what a lab can reasonably achieve. You know, it's always essential to make sure you're getting the calibration you need, and to look at the lab's measurement capability, uncertainty on their scope of accreditation. You know, per NIST, NIST says this is a quote directly from them, emphasizes that traceability alone does not signify or guarantee fitness for purpose, because this typically requires that the uncertainty associated with the measured value or calibration be sufficiently small to satisfy a particular measurement need. So check your calibration supplier, make sure you are getting what you need. So you take this, you start talking about traceability, we're traceable to SI, not NIST, and now we start looking at ASTM, which ASTM E74, people here must have interest, which is the standard practice for calibration and verification of force measuring instruments. So wording there is interesting. Force measuring instruments. Sometimes I'll use force measuring devices. Sometimes we'll call force proving instrument. ISO 376 calls it a force proving instrument. This one calls it a force measuring instrument. It's a lot of it is the same here. It's just, we all know we're talking about force transducers, load cells, proving rings, anything that can measure force. So there are some documents that reference E74. So if you're working to any of these standards, you're going to want to understand ASTM E74 as well. AASHTO T22, T68, ASTM E4, which I assume many people are doing. This is all over the world. The standard practice for force verification of testing machines. ASTM C39. Here are two that people don't get. Some people get, a lot of our customer base, we're doing a lot more calibrations because people are referencing ASTM E10 and E18, which make a call out for E74. And basically the call out is this document requires calibration by primary standards in accordance with ASTM E74. It is important as only the calibration laboratories with dead weights calibrated in accordance with ASTM E74 can calibrate these force measuring instruments and assign a Class AA verified range of forces as required by Section A 2.6.21. So basically, standard says you need to have your instruments calibrated in accordance with ASTM E74 by dead weights for verification. That's essentially what's going on there, and I would suggest read E10, E18 for more details. They both call out the Class AA verified range of forces. So we talk about a pyramid. Here's another pyramid. ASTM is built on test accuracy ratios, which a lot of people may say boo, boo, boo. However, when it is confined to a standard and people follow that standard, it can work really well. So what happens with E74 is they say primary standards are required to calibrate secondary standards. Primary standards can be used to calibrate working standards, as this will often result in the lowest possible loading ranges. So you may use it. You can use primary standards to calibrate anything below this on the pyramid. It's kind of hard with the testing machine, but it's still doable if you hang weights. Secondary standards are required to calibrate working standards. They cannot calibrate other secondary standards. So basically what it says, primary standards are 0.005, 50 parts per million. Then secondary standards, guess what? 0.05. That's a 10 to 1. So look what we're building here. We're building an accuracy ratio. Then secondary standards are used to calibrate working standards. Look at that, 0.5 to 0.25. That's a 5 to 1. See what they're doing here? Pretty ingenious. They're building in, and then these standards are used to calibrate a testing machine, which gives us I'm writing with my mouse, so it's a bit sloppy, gives us a 4 to 1. Look what they've done in this standard. Isn't that nice and sneaky? So your working standard has to be 4 times better than your testing machine. Then the standard to calibrate that working needs to be 5 times better. And then the secondary standards, that primary standards need to be at least 10 times better. Really, when it's confined and it works, and that's why you have to propagate correctly. So if somebody has a secondary standard with a Class AA and tries to calibrate another instrument and assign it, it doesn't work. Now we're not maintaining any type of test accuracy. In fact, we're propagating error that can be quite large as we soon approach one-to-one status, which is not good. So if we look at it, I'd said, primary force standard, the definition in E74 is a deadweight force applied directly without intervening mechanisms such as levers, hydraulic multipliers, or the like, whose mass has been determined by comparison with reference standards traceable to national standards of mass. To be classified as a primary standard, the masses of the weight shall be determined within 0.005%, that's 50 parts per million, of their values by comparison with reference standards traceable to the International System of Units. Hey, there we go again, SI, not traceable to NIST, for mass, ASTM E74, that's section 612 if you want to read it. And they require correction for the effects of local gravity, air buoyancy, must be adjusted to 50 parts per million or better. NIST weights are adjusted to within 5 ppm or 0.005%. Morehouse, we're typically better than 0.002%. And then per ASTM E74-18 section 6.1, they start talking about weight shall be made of rolled, forged, or cast metal. Adjustment cavity should be closed by threaded plugs or suitable seals. External surface of the weight shall have a roughness of 3.2 microinches or less, specified by ASME 46.1, which is interesting. And stainless steel is preferred. Why stainless steel? Because it's not magnetic. Any weight that can become magnetized can change. So if we use stainless steel, NPL, in the back of E74, there's a study where they did a 10-year study, and they found that if you're using non-magnetized weights, preferably stainless steel, that the drift on a deadweight machine is typically less than 0.2 parts per million. That is 0.2 parts per million. Very, very low. Very, very low. That just looking at these numbers up here. So we got 0.2 parts per million. Here, guess what? Right here, we're at 1 parts per million. So this is really where we're at. We're at 3 zeros and a 2. Actually, that's 2 parts per million. We're at 5 zeros and a 2. So, because if we're looking at, or 4 zeros and a 2, my math is off today. Really, NIST 5 parts per million is at the 4th decimal place. So that's where I started here. 4th decimal place is 1 part per million. The 5th decimal place is that 0.2. So this equates to 0.2 ppm. Parts per million when we talk about it. And that was using stainless, and that was a 10-year study on stability. So very, very good material, non-magnetic material preferred. Doesn't mean your interactions, the weights will not wear, grind. You have all kinds of things that go on when you're designing deadweight machines. We build them all the time. Our deadweight machines today are different than what we built 10 years ago. We are now stacking the weights inverted, so the largest weights are on the top, smallest on the bottom. This is just pure physics, a pendulum effect. We are building our machines more rigid. We just did maintenance on our machine to try to make it more rigid. We are doing things, plumb, level, square, rigid, low torsion. We are doing things that way. We are also the conical seats. We're trying to make the weights so when they hang, they always come back to the starting position, meaning, and there's enough gapping in there that you do not have to worry about things touching. All of this stuff over the years we have refined and perfected from the 1950s onward. Our machines, like I said, our machines today are much, much better than they were 10 years ago. In fact, our machine in our lab, we're building a machine right now for somebody else, and that's going to be better than the one that's in our lab. They're probably going to get better uncertainties than what we're doing just because we've made so many improvements as far as plumb, level, square, rigid, and plumb. We want everything to hang. We want the weights to hang. We don't want them to hang crooked or anything else. So we made enough modifications there. Secondary force standard, that definition, an instrument or mechanism, the calibration of which has been established by comparison with primary force standards. In order to perform calibrations in accordance with ASTM E74, your force standard must be calibrated with primary standards. The certificate should reference the standard used, and the associated uncertainties should be less than 0.005%. Some examples of secondary standards. Those calibrated by primary go to be our focus here. As one should understand, the calibration certificates for the load cells are shown in the pictures. Here we have 100,000 UCM. There's the reference standard, should be calibrated by primary. Here, interesting, we have our bench top, a 10,000 pound bench top. Depending what the use is, this could be calibrated by secondary in the UCM, or it could be calibrated by primary. We're showing it here doing a dynamometer. So in that case, either one's acceptable. The dead weight's going to give you the absolute lowest uncertainty. The lowest uncertainty is going to reduce the risk, which we're going to talk about in our next discussion. Not today, but our next discussion that will be available online as well, which is understanding calibration certificates, and we're going to talk about probability of false accept there. So really what you want to know, the easiest thing you can say is, if we draw something, the lower the uncertainty of the reference standard, the more room we have, or you could call this, people say, elbow room, the more room we have to be in tolerance. If we're using dead weight, we might have that much room. If we switch to secondary standards here, we might only have half the room to call an instrument intolerance or make a statement of conformity or compliance. So that's covered in another webinar. You can go look at the one on risk. We cover it on that one as well. And then we're talking about E74. So E74, we have to follow ISO 17025 guidelines. We also have to follow E74 guidelines on the calibration certificate. So here's some that, manufacturer identified, serial numbers, a lot of them overlap, but here there's some other things that may not overlap. And is the type of reference standard used in the calibration with a statement of the limiting errors or uncertainty. Listing of the calibration forces applied and the corresponding deflections at each rotational position, including the initial and return zero forces and measured deflections. 3.1.10, force measuring instrument resolution, the measurement uncertainty associated with the calibration results, and verified range of forces or verified range of forces. So that's another thing. And then this is one that trips people up. At least we have some new people in our company, and they say, hey, why do you have this statement on the certificate? And I've had other people say it too, because it's weird. But E74 says, hey, you're going to have to put a statement that the lower force limit expressed in the report applies only when the calibration equation is used to determine the force. It's not you. If you get an E74 calibration certificate, and we'll go to the next page. So what it's basically saying, hey, if I use this equation, this lower limit factor here is good. I cannot go take this device, program it into another meter with a 2-point span, a 5-point span, or something else, and claim that same lower limit factor. Basically, I'm going to add additional error by doing that. And we see a lot of people take these reports and then they go program them into something. Fine. It's just you're going to have additional error. When we talk about derating the device, that's additional error that you need to account for. So the lower limit factor is giving you that expected performance. Then you're not using the equation. And by not using the equation, you really can't go back on that lower limit factor unless you say, hey, in addition to that lower limit factor, I know I have this additional error of 0.02% or whatever that error may be. So now I got to take my expected performance, I got to take my other errors, and I got to figure out my uncertainty that way. So the best thing to possibly do is to use this equation. Use this equation, and then by using this equation, you will be in that you can almost guarantee that expected performance is going to be somewhat repeatable if you're using the right adapters and everything else along the way. So talking about E74, what we do, an instrument comes in our lab, we allow the UUT to come to room temperature. It typically will sit in our lab at least 24 hours. It would be nice if we could get everybody's instrument in and out within 24 hours, but typically we'll sit at least 5 to 7 days. In some cases, it may sit longer than 7. It just depends on workload, schedule, and everything else. So see this right here? That's calibration and issue date. That is now required for if you're accredited to the 2017 standard. So we're going to allow it to come to room temperature. It could be a 1 day in the lab. It could be 3 days in the lab. If it's a big 2 million pound load cell, we really want 3 days in the lab. If it's a 100-pound load cell, 1 day, 24 hours. So it gets put on a schedule, and then it gets plucked. And when it gets plucked, we say, hey, we're going to warm up the instrument. Typically 20 to 30 minutes. So we're going to turn it on, warm it up, let everything saturate, let it heat up, let the load cell heat up to the instrument. We're going to warm it up, 20 to 30 minutes. Then we're going to, by rights, while we're warming it up, we're going to select our test points and start doing all of this other stuff, getting things ready. Select the test points, 10 to 11, recommend 11. We'll go over that. Then we're going to fixture the UUT in the test frame. And when I said 20 minutes, here's why 20 minutes. We really want 30, but till we start selecting test points and we fixture it in the frame and we exercise it 2 to 4 times, it's going to be at 30 minutes. So exercise the UT 2 to 4 times, 2 is required. We typically will watch the ending 0 and see what it's up. We exercise, I can tell you in no case do we really exercise only 2 times. It's 3 to 4 for us in our lab. Takes a little extra time, but it really gets the instrument, especially after switching from tension to compression. You may need 4 exercise cycles to really warm up the material again or change that material. So after that, we're going to apply a first series of forces. Run 1. So we apply our forces. They're over here, and we record our outputs. I don't have the raw data. We record the output of the load cell. Then we rotate it. You see that says 0 degree over here. Then we rotate it 120, and we label it. We rotate it 120 from our starting position. That's clockwise orientation. Rotate it 120 degrees, and then we record the runs for run 2. This is kind of randomizing the conditions. If it's compression and tension, we switch to the other mode. And then we exercise, like I said, in this case, we're going to exercise probably 4 times to get everything out. And we'll do everything, if we're in the other mode, we do all of it, 1, 2, and 3 in the other mode. Then we switch back to the mode that we started in. So we switch back to the mode we started in, or this one was compression only. We just ignore this step and just go right to run 3, calibrate it, report it on the certificate, go run the data. At this point, we're looking for irregularities, and we're also comparing against previous data if we've had it. So do a lot of cross checks, and we've been more vigilant at trying to look at the lower limit factor. This one says 0.08. If the last time it was 0.1, we're like, yeah, we're good to go. We're lower than last time. If the last time it was 0.05, we're going to start doing checks. We're going to start looking at the data in more detail and make sure we didn't have a weird point or something else going on. So understanding the certificates, the measurement uncertainty of the measurement result presented in the same unit as the measure and determine relevant measurement percentage. So here we need to follow ILAC P14, which it says contributions to the inserted statement on the calibration certificate shall include relevant short-term contributions during calibration and contributions that can reasonably be attributed to the customer's device. Where applicable, the uncertainty shall cover the same contributions to uncertainty that were included in evaluation of CMC uncertainty component, except that the uncertainty components evaluated for the best existing device shall be replaced with those of the customer's device. Therefore, reported uncertainties tend to be larger than the uncertainty covered by the CMC. So short term is generally accepted that the repeatability and resolution of the unit under test be included. That is not reproducibility. ASTM lower limit factor best represents reproducibility. So we take the same things included when we did our CMC. We're doing a dead weight calibration. So in dead weights, we don't have a secondary standard with a lower limit factor. We have dead weight calibration by NIST. So we're going to take our CMC, which included repeatability studies of similar cells, and we're going to add the resolution to it. And we're going to report it. The expanded uncertainty is the aggregated uncertainty of the Morehouse measurement process, which includes the uncertainty of the reference standard used for calibration and the resolution. It is stated with a coverage factor of K equals 2 so that the confidence interval corresponds to approximately 95%. So at this point, we're going to start breaking down the certificate. What many people came for, and give a little bit of history. This is U resolution. Resolution of the force measuring instrument. It's calculated by dividing the force applied by the output of the load cell per point. Then an average of all those values is reported. So what we're going to do here, if we wanted to do this longhand or to break this down, some people say, how do you get this resolution down here? How do you get the 0.0121? Well, what we do for each and all of these force points, we take that and we take, basically on the average, and we divide it. So on this one, we say, if we wanted to know this resolution for 5,000 pounds, we take 5,000 pounds, the absolute value of 4 millivolts per volt, which that one, we divide 5,000 by 4 point, and we get 1208,776. So that's what we're getting right here. Absolute. This means 1 millivolt, 1 full millivolt equals 1,209.7766. Okay, that's good. That's 1 millivolt. Then we multiply by the readability. In this example, we are reading the force measuring instrument by 0.0001 millivolts per volt. If we were reading it by 2 counts, we would multiply by 0.0002. If 5, 0.005. So thus, here at the bottom, we multiply that 12 by, and we get 0.0120814, and we round that. Thus, the real resolution of this cell is 0.01208,774. Rounded, it is 0.0121. And if we take the average resolution, we would do this for each force point. So 100 divided by 0.8261 times 0.001, and so on. This page better shows what exactly we are doing and the variation. So absolute value millivolt output, resolution per 1 millivolt, multiplied by readability. At the end, see, this changed a little bit. Remember we looked at that? 0.01208 versus 0.01209. At the end, still didn't change this number. It just changed, we round up. So if you just do 1 point, you could end in a 4, and you could do all of them and maybe end in a 5, so you get a little bit of rounding, and you may see that. But if we look at this in a lot more detail here, you can see resolution per count is changing, 090909, there's 080808. It's this is really close. Though rounding the average, we still get the same answer here. So just something to look at. Then expanded uncertainty. In this example, we're using the certainty of the reference standard as listed on the scope of accreditation, as well as the short-term contributors for the unit under test. And there, I read this earlier, the expanded uncertainty is aggregate. So here we're looking at expanded uncertainty, what that's included, and we have to state that, roughly at a confidence interval that corresponds to, 95%. Looking at it in detail, made this neat little Excel sheet where we have UW is the maximum standard uncertainty for the calibration and measurement capability. URes is the resolution of the force measurements at the time of calibration. And this one is UV. This is interesting, is the standard uncertainty of the calibration of the voltage ratio measurement instrument used at Morehouse. This term is 0 for an indicator that is supplied with the transducer. So if someone sends us a load cell and says, hey, use your Agilent or 3458 or use your Fluke 8508, then certainty is going to get higher, and they're going to have to account for that. And because again, another potential error source in the voltage measurement. In this example, we did not use the voltage. So simply we set that to 0 up here. Look, UV indicator 0, 0. So what we're going to do here is typically we're going to take all of these contributors, and we're going to take the sum of the squares of these. So we're going to say 100 times 0.0016. We're going to take UW, and then we're going to take the resolution, URes, and we're going to take UC, and we're going to sum the squares of these, And when we sum the squares, so that essentially we're going to take, the square root of the sum of the squares, UW squared plus UV squared plus URes squared. And I need lessons because I'm running off the board, plus URes squared. And we're going to take that. We're going to take that sum of the squares, and we're going to then multiply that by the appropriate coverage factor. Right here, since we're dealing with, we want 95%, and we're dealing with virtually all type B data with, 200, basically 200 degrees of freedom. So we're dealing with type B, type AB data, reference standard resolutions, type B, some other ones, because these CMCs for our devices are a combination of AB, and the degrees of freedom are such that we're dealing with data about 200 degrees of freedom. We can multiply by 2 and know we will be at 95% confidence. So we take that, we take the sum of the squares, we multiply by 2, and we get uncertainties. And then here are uncertainties, and this is how they list. So 0.08, 0.08. If we wanted to find the percentage, we multiply this out. So 0.08, if we wanted to find the percentage, we take 0.08 divided by 5,000. So we can find the percentage in here. Say, what is 0.08 divided by 5,000? Well, it's 0.002. So if anybody wants this Excel sheet, we're happy to provide, this and those formulas. So calibration data coefficients here's a line on it. ASTM E74, ISO 376, and other standards may use calibration coefficients better to characterize the performance characteristics of continuous reading force equipment. These standards may use higher order fits, such as second order, third order. That's ISO 376. They only go to third order. ASTM E74 goes fifth order, as high as fifth order, as long as the force measuring instrument has 50,000 counts or more of resolution. Both standards use observed data, and they both fit the data to a curve. These higher order fits give instructions on how best to predict an output given a measured input in simple terms. So using least squares and higher order equations, here's from E74. A polynomial equation is fitted for calibration data by the least squares method to predict deflection values throughout the verified range of force. Such an equation compensates effectively for nonlinearity of the calibration curve. The standard deviation determined from the difference of each measured value is derived from the polynomial curve at the force. At that force provides a measure of the error of the data to the curve to fit equation. A statistical estimate called the lower limit factor, that's what the lower limit factor is derived from the calculated standard deviation and represents the width of the band of these deviations about the basic curve with a probability of approximately 99%. That was done. NIST did a whole bunch of testing and studies on this. The polynomial equation often uses higher order equations to minimize the error and best replicate the line. So we use that equation. Guess what? We don't care anymore about the nonlinearity spec of the load cell. We don't care. We're using a force equation. Doesn't matter to us. We're going to use that equation, and we're going to forget all about nonlinearity. Now, our next webinar, we'll talk more about nonlinearity and not using that equation, though this is E74, and E74 is predicated on using this equation to solve. So instead of using the equation for a straight line, y equals mx plus b, we have a formula that uses x values that are raised to higher powers, such as response, millivolt per volt, equals, and here's our formula, A0 plus A1 times the force, times F A squared F, and here's what we're looking at here, and so on and so on so on and so on. What we're looking at, A0 equals these coefficients, A1 equals that, A2 equals that, A3 equals this. These are often called coefficients on the they are often referred to as A0, A1, A2, A3. Oh. Then we look, the calibration report shows the formulas for solving for response and additional formula for solving for force. A lot of people call us and say, how do you get the B coefficients? Easy. The formula for force is found by switching the X and Y axis. If one wanted to generate coefficients to solve for force or find the B coefficients, one would use the predicted response for the X axis and force for the Y values. Simple as that. You know, we have a spreadsheet available for download that will use these formulas to help interpolate values that are not on the calibration certificate. That spreadsheet can be found here, right here. And it's a pretty simple spreadsheet. You can convert pounds to kilograms and some other stuff, but you enter your coefficients right here. We're entering these values. We're entering these values at zero force. This is really what I want to show people. So the A0 coefficient here is negative point what? 0.000027. That is up here. Now up here is rounded. So at 0, that means at 0 force applied, we expect our indicator to read 0.00003. Well, actually, we don't expect the indicator to read that. We expect that if we put in 0 into the equation, that's what we will get. We will tear the indicator. However, if we look at the B coefficients here, look at this. This is where we're solving for pounds. So at 0, when the millivolt per volt value is at 0, we are not at 0 in pounds. We are at this B coefficient, which is negative 0.03. So if we put this on a meter and we tear the meter so that we're reading 0.0000 millivolts, our display should read, when we use this equation, negative 0.03, right? So down here in the predicted response, I show that. So what happens when we put in negative 0.0003? We read 0. So that is the exact same as up here. At negative 0.0003, we expect, if we use this equation, to read 0. And then what essentially happens is this formula, this B coefficient, works from the calibrated force values. So if we start calibrating at 100 pounds, it will work from 100 pounds. You may have a negative 0.03 offset. That's how the math works, right? It is just how it works. This is where it starts. These are the instructions for curve fitting. You should not be able to use this device below its first calibrated point. And hence, a lot of people get thrown that say, hey, when I zero the meter, I expect it to read 0. And my answer is always going to be, at 0 force, the predicted response is this, and at 0 response, the unit will read whatever the B0 coefficient is. So when we're using that B equation, when we put 0 through it, see, nothing is clearing out. So this is basically the B0 plus BR. R is the response. So that this number becomes 0 at 0. This number becomes 0 at 0. This number becomes 0 at 0. But the B0 isn't multiplied by any response. So therefore, when that indicator is zeroed out, whatever the B0 value is what the indicator will read when using that equation. So what this relationship of force versus response at very low responses, here we go. They are found by simply curve fitting the average of multiple runs and the force applied. If you want to do this in Excel, it has a line test function. One can also graph the X and Y values and click add a trend line and then display the equation on the chart. That's essentially what we're doing here. And I'm going to go show it. Look where this is starting. Look at that position. It's not 0, 0. It's starting slightly off. So we further go into this. Like I was saying before, many customers want to see 0 displayed on the device when they zero an instrument. It's not how it works. In this example, when the meter reads 0, the force is this. And you can see this right up here. That's not 0, 0. the force will be this. LBF, or sometimes a rounded number, like, 0.3, which would be negative 0.3 if the B0 is this. The reason right here, the reason is the equation, and look, B0, again, this B0 is not multiplying by your 0. So there's what it is. So simply put, B1 and 2 and higher are multiplied by the 0 on the meter, except for the first one. The meter will read 0.0 when the response is equal to this. Negative 0.0003, because we're not reading the 6th decimal. We're actually reading it there. So and if you notice, the line doesn't start at 0. So therefore, and it's probably, your device is probably not going to read right for the first 10 pounds on this load cell. Really, we didn't start the calibration till 100, so you can't trust it. You cannot trust any reading below 100. But at 100, it darn well better read what the calibration reports it says it's going to read. And that's going to be within whatever, it's going to read plus or minus whatever the lower limit factor is. So looking more at curve fits, deviation from the fitted curve, these are the differences between the fitted curve and the observed values. This is what we're looking at here. Because if we just plot that line, we don't see much. If we plot a line over line, we don't see much. So we choose to plot the deviations here. And what we do here, selecting the right degree fit, ASTM has an annex. So you say, hey, I have more than 50,000 counts of resolution. How do I dissect the right degree fit? And that's A13 of the annex, which says fit separate polynomials of degree 1, 2, 3, 4, and 5 to the mean data. Denote the computed residual standard deviations by S1, S2, and there's the formula. So really, it has a procedure for determining the degree of best fitting polynomial. If the customer can handle a higher than secondary, Morehouse follows the ASTM E74 annex. We use the F constants using the 97.5 table, using the mean for the F test. There's ways to do this formulatically. And then you look at the lower limit factor used to calculate the lower end of the verified range of forces. That's section 8.5. Other factors evaluated in establishing the lower limit or verified range of forces are the resolution of the instrument and the lowest non-zero force point in the calibration force sequence. The lower limit factor is one component of measurement uncertainty. So basically what I'm saying here, our resolution is 0.0121. ASTM says, hey, your first force point cannot be less than 400 times the resolution. Just can't. And 0 is not a calibrated test point. So 400 times the resolution is as low as we possibly can go. It also makes a recommendation of a 2% point. So right here, we're choosing the 2% point. So any customer, theoretically, 400 times the resolution is the first force point we could calibrate. And then the other thought of this equation is 400 times the lower limit factor is going to be the first point in the verified range of forces, which we'll cover that later. In this example, the customer, if we would have taken a low enough force point, they could have driven this cell down to about 32, 33 pounds. So since we started at 100, guess what? The Class A verified range of forces has to start at 100. If we look in more detail here, you have the data analysis, which we're going to go over what we're doing. Deviations from the fitted curve. These are the differences between the fitted curve and observed values. The standard deviation is the square root of the sum of all the deviations squared divided by n minus 1. This is a little bit strange for those that have statistics. You're basically taking that degree curve fit and creating a little bit of a penalty here. So if I'm using a 5th order and I have 33 force points, I'm going 33. Our points here, we took 33 points because some people only take 10. That's not good because how low can you use your instrument? You cannot use it below 400 times the lower limit factor or the first non-zero test point. So if someone starts at 500, the best they can do is use this device from 500 to 5,000. Morehouse, we took a 100, so the best they can do is use it from 100. In practice, they could have used it from like 33 based on this data. So 33 minus 5 minus 1. If we use a 5th order. We didn't use a 5th order in this equation. We used a 3rd order, so we do third. So that penalizes you instead of your n minus 1 that most people want to see. A little bit, so you get a little bit of penalty for higher order. So we do all this. We take all these deviations, and guess what? Hey, we're summing the squares. So we're summing the square of the square root. So we're taking the square root of the sum of the squares of all these divided by n minus m minus 1. That's going to give us our standard deviation, which we then multiply our standard deviation. The lower limit factor is 2.4 times the standard deviation, and we get that by figuring out our resolution again, because we're in millivolts. We're going to get a standard deviation in millivolt, and we're going to convert it to, in this case, we're going to convert it to LBF. So we're going to multiply it. We're going to convert it by, we're going to take that resolution equation, and we're going to multiply it and convert it. The Class A range is 400 times the LLF. The Class AA range is 2,000 times the LLF, as seen right here. And here's some more things we're looking at change from previous. But look, Class A, 100. Class AA, 175, because we're multiplying by 2,000. What that Class A does, the brilliance of multiplying this by 400 gives us a built-in 4-to-1 on our testing machine. At this first force point, if it multiplies out, it is going to be either better than 4-to-1 or at 4-to-1. In this scenario, it's better than 4-to-1 because our real first test point would be like 33 pounds of force. At that point, we would be 4-to-1. However, we didn't calibrate it down that low, so we can't use it that low. And therefore 1. At Class AA, this one does work. So we take Class AA times 2,000, and guess what that gives us? If we calibrate another instrument to Class A, that's going to build in a 5-to-1 scenario where we're going to be 5 times better at that first force point than what we're calibrating. Really, really cool stuff here. In addition to that, we start looking at change from previous on the data. On this data set. That's another thing that you want to consider when you do your uncertainty. You want to consider the stability. Lots of ways to do this. You can use just one set of data. This would be type B, or you can use multiple types of data. One calibration to the next is typically what we see a lot of people plug these numbers in. Then ASTM says, why 30 points? People ask, why? And you know what? It's simple. The rate of change in the standard error approaches 0 at about 30 samples. This is why 30 samples is often recommending when generating summary statistics, such as the mean and standard deviation. Also the point at which the T and Z distributions come nearly equivalent. So right here, standard error and sample size, you start really, there's arguments for 24, but at 30, it reaches diminishing returns. We do 33, and we do 33 so we can get that first force point lower than 10%. But after 30, it's really diminishing returns. So more about E74. The Class A or Class AA verified range of forces cannot be less than the first applied non-zero force point. As I said earlier, that means we're 100. And this, see, I was saying 33. My math was bad. It's 34.96. So 400 times 0.0, 34.96. Theoretically, the customer could have used this cell. If our first force point would have been 34 pounds, they could have used it from 34.96 to 5,000. We chose to do the 2%. E74 is clear on this. The verified range of forces shall not include forces outside the range of forces applied during the calibration. If the lower force limit is less than the lowest non-zero calibrated force applied, then the lower force limit of verified range of forces is equal to the lowest calibration force. That's what's happening right here. Here's that standard deviation that we're getting from that formula, 0.00000301 millivolts. Convert that to pounds, and we get that. So really, we see people violate this section 862 all the time. They report lower limits less than the first non-zero force point. It is wrong. It is not correct. And in that calibration below that is not valid. So here, it's recommended that the lower force limit not be less than 2%, 150 of capacity per the instrument. So that's a recommendation. Unless someone tells us, hey, I want you to do a 1% point, I want you to go lower, we're going to follow the recommended guidelines. For section 721, if the lower force limit of the verified range of force measuring instrument is anticipated to be less than 1/10 of the maximum force applied during calibration, 10%, Then forces should be applied at or below this force limit. In no case should the smallest force applied be below the lower force limit of the force measuring instrument as defined by 400 times the resolution for class A verified range of forces, 2000 for AA. So that's another one. This report had class A and AA. Therefore, we got to take 2000 times, that resolution, which, that's around 50 some. So, calibration procedure, criteria for verified range of forces, lower limit factor is 2.4 times the standard deviation converted to force units, multiplied by the average resolution. Here we're doing that right now. People are probably saying, hey, what's this? When is it going to talk about this? So here's the math, 2.4 times this. We're going to take 0.00301, multiply it by 1209. Remember, if we just did by the capacity point, we would have been at 1208, slightly different, slightly lower. So we're going to multiply it by the average of all of them. And that corresponds to what we get, lower limit factor of 0.08736. And we reported it on our cert of 0.0874. It's based on the LLF or resolution, whichever is higher. The class A 400 times the LLF or resolution, class AA 2000 times. Any force measuring instrument that is either modified or repaired should be recalibrated. That's per the standard. And recalibration is required for a permanent zero shift exceeding 1% of full scale. So say you overload the load cell. If you shifted the zero by more than 1%, you probably damaged the cell. You could have it recalibrated, but if you have a zero shift of, let's say your zero shift is, at that 1%, you're going to have additional error. Anytime you shift the zero, you're going to have additional error. So if you overload it, it should be recalibrated, even if it's not exceeding, even if it's below the 1%, still additional error. The output can change depending on how you need, how low you need that uncertainty, because if it is overloaded and you go with it for a year of data, you could be issuing some recalls there, depending what you're claiming. Calibration interval, wanted to talk about this. I hit on it earlier. So 11.2.1 basically says force measuring instruments shall demonstrate changes in calibration values over the range of use during the recalibration interval of less than 0.032% of reading for force measuring instruments and systems used over the class AA verified range of forces, and less than 0.16 of reading for those instruments and systems used over the class A verified range of forces. 11.2.2 force measuring instruments not meeting the stability criteria of 11.2.1 shall be recalibrated at intervals that shall ensure the stability criteria are not exceeded during the recalibration interval. So there's this. In this scenario here, look, our class AA, this first point here, class AA doesn't meet the 032, though that was 100 pounds. We're okay because our class AA range is 175, which then would meet. So here's something else we do. NIST gives an annex, and we decided we like NIST. We really like them. So we take a similar approach to measurement uncertainty, which is done in the annex here. This is right here. Here's our sample. If you've seen a NIST cert, NIST looks very, very similar. We copied a lot of it. Don't make many mistakes about it. They follow Technical Note 1297, or Technical Note from NIST. Very, very good method to say, hey, this is really, with that lower limit factor, this is really that true expected performance of the device here, and we know you're going to derate it, but it includes the lower limit factor and includes the uncertainty of the reference standard. So it's the value of how good the force measurement is at the time of calibration. It is a representation of the expected performance of the force measuring instrument under similar conditions using machines that have similar characteristics of being plumb, level, square, rigid, and low torsion. It would include any adapters or fixturing sent in by the customer. The end user will still need to perform an assessment of their loading conditions and determine if additional error sources exist, which all the time they usually do. So here's what we do here. When we report expanded uncertainty, we use the following formula: combined standard uncertainty, right here, this formula right here. And we went over this earlier, where UR is the standard deviation. What we've added here is UR. That thing we did earlier where we reported an uncertainty, we only used UW, URES, and UV. Here we're adding in the lower limit factor in the appendix. So UR is the standard deviation calculated from the differences between the individual measured responses and the corresponding responses computed from the calibration coefficients. So what we do here, going back to another Excel sheet, we take, there's UW, that's ours, dead weight machine, 16 ppm, multiply it by the force, and we get these numbers. Then we take UV, which is the standard deviation here. This is the LLF. Actually, it's not the LLF, it's the standard deviation. Take the resolution per 1 millivolt, right? And we report, this was going to be voltage, this should not be here. And we report that standard UR in force units as 0.036 the whole way down. That UV, that would have been there if we had voltage. We would have had something indicator that would have been here with the indicator that we're okay. So this is the standard deviation. This is our true UR right here. I condensed and hid some files. So UR resolution per 1 millivolt, multiply it out. There we have UV. There we have what we have, 036. UUT, it's constant because the lower limit factor is constant for the whole loading range. Then you have the resolution, and now you combine them. UC is combined. So we combine everything. We sum the squares of all of this stuff, and we multiply it by k equals 2, and by multiplying it we get u. We get our uncertainty here that varies, and you can see it's varies. And then if we wanted to take it as a percentage, what we do, we take this uncertainty and we divide by this number. So that 0.108 divided by 5,000 as a percentage, 0.002. We report that on our certificate here too. 0.002% of max response. And if you look at this compression loading, it says U equals 0.009 response units. That's over here. So there we go. We take 0.022, multiply that by the millivolt output. That gives us the response. So that's what we're doing. The end user will still need to do more thorough analysis on uncertainty for their ABS guidelines, which will include compliance to ILAC P14, which in section 5.1, uncertainties to be calculated per JCGM, the GUM, and we have a tool to help meet compliance with the GUM. Though again, when we say compression loading, this is exactly what we're doing. We're taking the sum of the squares of all the individuals for that formula, and we're coming up with a percentage of max response. So really, this device was calibrated by our dead weights, good to 0.0016, and at the end, we're saying, hey, this device at capacity, this load cell 0.002. But if we go look at the small, if we go look at down at 100, it's 0.07. At 500, it's 0.0147. This is where we get into the secondary standards. You say, hey, can one load cell do it all? If you're using as secondary standards and want to maintain better than 0.02, more than likely, you're only going to, maximum you're going to be able to get is from 10%, 10 to 20% of the loading range. And therefore, someone buys like a PCM or other machine, we usually recommend 2 to 3 load cells because you're going to have to switch up depending on what you want to maintain. If you want to maintain better than 0.01 for some ISO requirements, you're going to have to do a whole heck of a lot more. Anyway, going on, we had that paper on uncertainty, and typically when we're looking at uncertainty for force, it doesn't end with what I just showed you of the 002. You have to get that device. You're accredited. You have to get it, and now you have to do more. And this is the more that most people do. You're going to take your type A, which is going to be the ASTM lower limit factor, reduced to 1 standard deviation. You're going to take you're going to do a repeatability study of the best existing device. You may do a repeatability and reproducibility between technicians. Our sheet has that built in. Then you're going to use type B contributors. Since we use dead weight, you're using a load cell that we calibrated for you, you're going to have to use the resolution of that load cell, reference standard resolution. Dead weight says if applicable, which is 0 with a dead weight because it's a relatively known weight. And then you're gonna do your repeatability study with another load cell. Preferably, you buy a really, really good load cell to do this repeatability study if you're using a PCM or something else, and then you use it as an artifact to do your ILCs, inter-laboratory comparisons, and a lot of other things. Then you're going to take the reference standard uncertainty and stability. Remember, we talked about drift. These are all other things. Stability can be a type A depending on how you use it. And environmental factors such as temperature, other error sources, maybe have some side loading and some other stuff. You're going to take all of this stuff and you're going to run it through the Welch-Satherthwaite equation. And if you're going to do that, you're going to need a calibration report for the device, the uncertainty of the instruments that were used to perform the calibration. They're right here. This is why we do this. We put these all there. So temperature standard, not so much. I'm probably not going to need that. We're basically saying we're within 0.2. You're gonna more than likely hold to 0.1 degrees. So you're gonna figure that on your environmental factors, or maybe you're holding to 2 degrees. I don't know. Whatever you're using, you plug it all in the formula. But so this one is 0.0016 of applied force. For this, that's the uncertainty of the standards performed history. Calibration history, that's changed from previous. Manufacturer specification, we like to use this for environmental. It'll give you what to use. Error sources if known, and then we say the end user is going to have to do a repeatability study, R&R between technicians. And if you're accredited, you're going to have a program to complete proficiency testing requirements. This is where if you buy that second load cell, like a mid-range, and you can do a lot of stuff with that second load cell. You can use it for ILCs. You can use it as a check standard. Highly recommended. There's times we get load cells in our lab and they're just not working right. And we're like, is it us? Is it the machine? And having that check standard, you put it up in and say, nope, not us. It's that, right? Without that check standard, you really can't point to it. And you want to make sure you're maintaining. Different things happen. What if a tech changes out an adapter? The check standard, you can check different adapters there too. You can say, oh, guess what? We're not repeating. What did someone do? Hey, that sneaky person changed out an adapter. That sneaky person did something with, the cable. It's just there's so many good practices here to have check standards. So this is the sheet. There's more detail on it. We have measurement uncertainty training.info is a website that has a lot more information on it, or you can just download it from our website. Website download is right here for anybody taking this, though you can also go to measurementuncertainty.info. And here we have what it's going to do. It's going to give you uncertainty per point. You can use right here, there's only 2 points. Ideally, you would use a lot more than 2 points, and you can see percentages. Here, this was in a PCM with just one load cell. We were hitting 022. If you wanted to hit better than 02, you would need 2 load cells. But at capacity, we were better than 00551. So some might take all these, and it'll do expanded uncertainty. Multiple points, you can enter multiple things. Really, really a good tool. And when we talk about measurement uncertainty, if we examine it, Morehouse versus another accredited supplier, look at what happens. Look at all this stuff here. Accredited supplier, look at these graphs. What's stability of the reference standard when Morehouse calibrates something is really, this is usually the highest, but look at here, stability, and you got to look at these numbers. So what we're really looking at, expanded uncertainty at 10K on a 10K load cell is 0.41 pounds of force when Morehouse calibrates it, and we have a CMC of 0.16, 0.0016% times 10,000. Repeatability was this. And if we look at the accredited supplier, they're starting at 4 pounds. Repeatability point this, expanded uncertainty 4.3. So what really happens here is the starting point's a lot higher, and therefore your uncertainty is higher, and your expanded uncertainty when calibrated with primary standards is really approximately 10 times lower than using secondary standards on good load cells. On load cells that aren't as repeatable, it can be, it can be 20 times lower. It can be all kinds of multiples. So decreasing loads, as much as I want to keep talking about, primary standards and calibrations Morehouse offers, it's easy. It's easy to me. You get better results when you use standards with lower uncertainties. Descending load, here we go. Predicted response comparing ascending versus descending. If you look at this, here's the same load cell. And this customer had us calibrate this load cell ascending and descending. If we look at the difference on the force point between 100 pounds, the ascending curve gives us 0.082267. Descending curve gives us 0.0827. Difference of 9 counts. And that is a percentage difference of 0.107. Here at 500, 0.114. And if you look at capacity, there's really no difference. We have to go back up to capacity to descend. So that's why you would have a slight difference, because we have to, we're using a slightly different curve and data set if we're fitting to the descending curve. So when we look at descending right here, we have these differences. So if a load cell is going to be used to make descending measurements, it has to also be calibrated in descending mode. And that's really the point. A difference on, good 5K load cell like we're seeing, using the ascending only curve would add an additional error of about 0.05%. And that's basically saying, hey, my ascending point is this, and my descending point is this. The difference between this curve and that curve is 0.05%. And not to mention, ASTM E74 section 7.41 deals with it, and it says force measuring instruments are usually used under increasing forces, but if a force measuring instrument is to be used under decreasing force, it shall be calibrated under decreasing forces as well as under increasing force. Use the procedures for calibration and analysis of data given in section 7 and 8, except when otherwise noted. When a force measuring instrument is calibrated with both increasing and decreasing forces, the same force values should be applied for the increasing and decreasing directions of the force application, but separate calibration should be developed. What we say, if a force measuring device is to be used to measure forces during decreasing load sequence, then it must be calibrated in that matter. Separate calibration curves can be used for ascending values and descending values. A combined curve can also be used, though the standard deviation is going to be higher, meaning your lower limit factor is going to be higher. Typically, if you need to use a curve, and why one would do this is they might say, hey, I just want to go to 30% and back down. That's fine. But to do that, you're going to have to take the penalty of fitting the entire curve. So the LLF for a combined curve will typically be 3 to 4 times larger than the LLF of an increasing only calibration. We just showed the difference was 0.05. A descending curve is only valid if the device is loaded to full capacity. That's true. That's the reason you do it. That's the reason you use a combined curve, because we're going to capture all this error, and we can go to 50% back down. Right there, I just showed my drawing was off. But if we go, this is the increasing. If we go up to 50%, typically we come back down. It's going to go like this. Kind of starts looking like a whale after a while, depending on how you draw these. And then it's one of those things. If you cannot go to capacity each time, the combined curve, you're going to just live with a larger lower limit factors, which is going to give you a larger uncertainty for ascending, descending. An ascending curve can be used for increasing calibration. We always recommend doing that. So if you're using ascending, and if you need to make descending measurements and you're not always going to go to capacity, we recommend using the ascending curve for ascending measurements and then the combined curve for ascending, descending. Combined curve would be recommended for any descending values, as the user would not have to apply the maximum force. Well, that's it. Longer webinar than some of them, because I wanted to really to really go over the E74 cals and how you're doing some of the data. I would strongly ask everyone, if you haven't, subscribe to the Morehouse Insider and stay up to date on the latest indices, trends, upcoming events, and calibration tips, or follow us on LinkedIn. Follow us on LinkedIn. Like us on Facebook. We're really looking on LinkedIn to build that subscriber base because we're making announcements there. We're posting things, cartoons, some other stuff. Our next webinar is December 8th. And if you're watching this via video and it's past December 8th, 2020, you can just go to YouTube and find it. It's the cover single run calibrations with it and without tolerance specifications. The without specifications covers calculating performance characteristics such as nonlinearity, hysteresis, and SEB, and how to calculate resolution and expanded uncertainty. We did that. We did a lot of that today. The with tolerance specification covers what pass-fail statements of conformity are and how to calculate TUR, test uncertainty ratio, and PFA, probability of false accept. Excuse me. Follow us on social media and contact any questions. Contact us at info@mhforce.com. I certainly hope everybody had learned something from this. Your time is valuable. If you're watching it or here live or whatever way it means your preference to digest this data is, I thank you for listening to us in your time. Hopefully you learned something. May everyone be safe, and may your calibrations have the lowest uncertainty probable. And to do that, may they be calibrated, hopefully by Morehouse with deadweight primary standards. Thank you all. Take care.